NASA's Voyager 1 spacecraft, which currently holds the record for the most distant object ever constructed by humans, has fascinated individuals globally for nearly 5 decades since its launch. Voyager 1 has transmitted vital data from the farthest reaches of outer space, enhancing humanity's understanding of the universe. However, the probe's recent transmissions have exhibited unusual anomalies that have left specialists perplexed. The mysterious signals have ignited intense discussions, prompting the scientific community to question whether these irregularities are mere technical malfunctions or signs of something far more extraordinary, potentially even extraterrestrial involvement. Join us as we explore these perplexing messages and investigate what might be hidden in the vast expanse of the cosmos. The intrinsic human desire to uncover mysteries has long driven our quest for space exploration. This profound curiosity paved the way for ambitious projects such as Pioneer 10 and Pioneer 11, which were among the most daring space missions of their era. On August 20th, 1977, the launch of Voyager 2 from NASA's Kennedy Space Center marked the beginning of a groundbreaking era in space research. Shortly thereafter, on September 5, 1977, Voyager 1 was dispatched into space, embarking on a journey that would lead it to the outer planets, dramatically altering its trajectory and scientific outcomes. Probe with a mass of approximately 721 kg, comparable to a compact automobile, traveled in distinct directions at varying speeds. On December 15, 1977, a significant milestone was achieved when Voyager 1 surpassed its twin in terms of distance covered due to their divergent paths. Since then, Voyager 1 has served as a crucial asset in deepening our perception of space, providing discoveries that have transformed our understanding of the universe. Before delving into some of its recent groundbreaking findings, let's revisit several of its earlier key accomplishments. In 1979, positioned roughly 265 million kilometers from Earth, Voyager 1 captured high-resolution images of Jupiter. By January of that year, had completed an impressive 100-hour study resulting in a time-lapse sequence that depicted Jupiter's rotation. A set of 3,750 images offered unparalleled insights into the planet's turbulent atmosphere and complex features. During this mission, Voyager 1 also detected a previously unidentified ring around Jupiter and discovered 2 unknown moons, significantly enhancing our knowledge of the gas giant's intricate system. To maintain its course and avoid colliding with Titan, one of Saturn's moons, the probe performed several navigational adjustments. Subsequently, the mission shifted its focus beyond the solar system's planets as the spacecraft was redirected into interstellar space, traveling at an extraordinary pace of 325 million kilometers per year. NASA +2. Space +2. NASA Science +2. January 1990, Voyager 1 commenced its assignment to explore interstellar space, pressing onward beyond the confines of our solar system. During this phase, it accomplished several exceptional feats such as identifying for new moons, Mimes and Enceladus, Tuz and Rhea, and capturing some of the most memorable images of the solar system's outer boundaries. On February 14, 1990, located approximately 6 billion kilometers from the Sun, Voyager 1 took the iconic family portrait, a panoramic collection of images of the inner planets. This compilation of 60 photographs was added to the probe's extensive gallery, which already featured hundreds of images from its close encounters with the gas giants. Voyager 2, in parallel, achieved remarkable milestones during its journey. It measured wind speeds on Neptune that topped 2,100 km/h, roughly 1,300 meters per second, the fastest atmospheric currents ever recorded in the solar system. It also observed Triton, Neptune's largest moon, where temperatures plummeted to a frigidus 391 degrees Fahrenheit, 235 degrees, ranking it among the coldest known locations. Triton exhibited signs of icy eruptions spewing nitrogen gas and frozen debris up to 5 kilometers high, revealing fascinating new aspects of its geology. These extraordinary discoveries significantly broadened our understanding of the diverse and dynamic conditions in the solar system's outer regions. The impact of both Voyager 1 and Voyager 2 has been truly transformative. Their findings unveiled previously concealed characteristics of Jupiter and Saturn's moons. To be inactive, this new evidence redefined beliefs about their geological activity. Voyager 2, in particular, made history as the only spacecraft to date to pass close to both Uranus and Neptune, an unparalleled achievement. NASA employed a series of innovative strategies to extend the lifespans of these groundbreaking missions, such as powering down non-essential components to conserve energy. The endeavor is projected to continue until 2030, symbolizing the conclusion of a remarkable chapter for the teams who dedicated themselves to this mission. The construction of Voyager 1 and Voyager 2 exemplified advanced design and engineering. Built to rotate slowly, these probes minimized motion blur in their images during travel. Even before arriving at the outer planets, the spacecraft began relaying detailed visuals of Jupiter, unveiling its swirling clouds and the well-known Great Red Spot, a colossal storm that has piqued scientists' interest for decades. One of the most thrilling discoveries was the detection of active volcanoes on Jupiter's moon Io. Discovery. The instruments aboard the spacecraft picked up peculiar readings from the moon, later validated by images revealing massive volcanic plumes and a violently reshaped surface. One eruption on Io was found to be 1,000 times more forceful than Mount St. Helens, blanketing an area nearly the size of France. As their voyages continued, both spacecraft were gradually powered down to save fuel before heading into interstellar space. Strikingly, they didn't capture images of Mercury or Mars due to technical constraints. NASA later launched additional noteworthy missions, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11 to become the most distant probe from Earth. Nevertheless, Voyager 1 continued its journey for another 14 years before officially penetrating interstellar space on August 25, 2012. The pivotal factor in the triumph of these missions was the strategic utilization of gravitational slingshot maneuvers, which propelled the spacecraft toward their objectives while conserving fuel, rather than depending entirely on propulsion systems. They harnessed planetary gravity to gain velocity and alter their courses. This technique enabled them to span colossal distances with minimal fuel expenditure. As Voyager 1 approached Jupiter, the planet's immense gravity accelerated the spacecraft. Precision was essential to avoid hazardous changes in speed or trajectory. These gravitational boosts allowed the probes to expertly traverse the solar system. Voyager 2 likewise exploited gravitational pulls from Jupiter and Saturn to propel itself toward Uranus and Neptune, validating the efficiency of this navigation. Reflecting on these extraordinary undertakings, the scientific community eagerly awaits further insights from the anomalous transmissions recently detected by Voyager 1. These spacecraft continue functioning far beyond the solar system's known perimeter, probing the mysteries of planets like Jupiter, Saturn, Uranus, and Neptune. Voyager 1's time-lapse sequences vividly documented 10 eruptions on Jupiter and revealed new satellites as well as a previously unrecognized ring encircling the planet. These revelations significantly enriched our understanding of the Jovian system. Similarly, Voyager 1 discovered 4 additional moons orbiting Saturn, Mimes, Enceladus, Tethys, and Rhea, while also providing breathtaking visuals of the planet and its rings, illuminating their elaborate structures. The missions, expeditions to Uranus and Neptune, yielded critical observations about their atmospheres and satellites, enhancing our grasp of the solar system's distant territories. After finishing their planetary flybys, both probes set course for interstellar space, where they persist in collecting crucial scientific data. This ongoing investigation widens our perspective on what exists beyond our solar neighborhood as we await new developments regarding Voyager 1's peculiar emissions and their implications for our understanding of the cosmos. The incredible journeys of these probes continue to inspire both researchers and enthusiasts globally. Their accomplishments remain foundational in expanding human knowledge and pushing the boundaries of space science. The Voyager programs have delivered unprecedented glimpses of our solar system in regions far beyond, offering iconic imagery and valuable scientific results. In addition to their empirical contributions, the spacecraft carry a symbolic artifact, a message crafted to represent Earth to potential extraterrestrial civilizations. The Golden Record contains greetings in 55 languages, musical pieces from various cultures, and natural sounds such as thunder and whale songs. Interstellar Communicate serves as humanity's hopeful attempt to communicate with intelligent life beyond. Voyager 1 and 2 were outfitted with an array of scientific instruments that significantly enhanced our comprehension of space. These included magnetometers, plasma wave sensors, and imaging tools, all of which supplied critical data about space environments. The magnetometers helped unravel the magnetic fields of Jupiter, Saturn, Uranus, and Neptune, revealing how these fields interact with their surroundings. Plasma wave detectors clarified the influence of solar winds on planetary atmospheres. One of the mission's standout achievements was charting the boundary of the heliosphere, a vast region populated by solar particles and electromagnetic fields that envelopes our solar system. As Voyager 1 approached this boundary, it observed a transition from solar wind to interstellar material, yielding essential insights into how this barrier protects Earth from cosmic rays. The spacecraft pinpointed a location called the termination shock, where solar winds decelerate and condense. Beyond that lies the helio sheath, a turbulent region where solar and interstellar particles collide, creating a dynamic environment. Voyager 2's expedition also greatly enhanced our comprehension of the outer solar system. Close pass by the giant planets offered critical observations, especially regarding Uranus's magnetic field, which was found to be inclined in an unexpected manner that defied existing theories. The findings have stimulated further research into planetary magnetism. The endeavors not only advanced scientific insight but also rekindled public fascination with space exploration. The mesmerizing images of distant planets and the captivating stories behind these missions have inspired countless individuals across generations. Iconic visuals like Saturn's elegant rings and Jupiter's volcanic moons have become emblematic, encouraging new scientists and aspiring explorers. As the Voyager spacecraft persist in transmitting exceptional information, their prolonged exploration of interstellar realms offers unmatched opportunities to decipher the fundamental nature of the universe. Although prior emphasis was often placed on the planets within our solar system, delving into interstellar regions has revealed surprising complexity. Zones once presumed void are now known to exhibit intricate phenomena that challenge current scientific paradigms. Among the most captivating findings is the detection of cosmic rays originating from beyond our solar system. These highly energized particles, traveling nearly at the speed of light, provide clues about processes occurring in remote parts of the galaxy. Examining their energy levels and composition, scientists aim to better comprehend the dynamics of distant stellar nurseries and galactic behavior. Moreover, as Voyager 1 and 2 delve deeper into interstellar territory, their onboard instruments continue to evaluate the density and movement of the interstellar medium, the diffuse matter that occupies space between stars. The medium composed of gas and dust interacts with the solar wind and shapes the heliosphere's configuration. As the probes navigate through it, they relay invaluable information that assists researchers in modeling how energy and matter operate across cosmic distances. In addition to these contributions, the Voyager missions have unveiled essential details about magnetic fields in interstellar space, shedding light on their properties and influence. The revelations could eventually drive breakthroughs in understanding magnetic forces throughout the galaxy. The ongoing exploration of these distant frontiers not only extends our scientific awareness but also motivates future generations of space scientists and engineers. The unforgettable images obtained by Voyager, especially the renowned pale blue showing Earth from over 6 billion kilometers away, serve as a humbling reminder of our tiny presence in the cosmos. These photographs, combined with the mission's scientific accomplishments, have deeply reshaped how we perceive our world and its position in the universe. The success of the Voyager missions has paved the way for even more ambitious ventures, thanks to the advancements developed during their expeditions, launching sophisticated probes to more remote corners of the galaxy is increasingly achievable. Ambitions like exploring exoplanets, identifying potentially habitable worlds, and even interstellar travel are steadily evolving from visionary concepts into practical objectives for the future of cosmic